So now we're on to question 5, assignment 1. You know, what's kind of ironic, I'm looking at this question, and maybe it's the wording or whatever, but at the end of the day, what this is basically wanting you to do is you've got 4 different temperatures. Boyle's law. So Boyle's law at the end of the day was essentially P times V equaled some sort of constant. Now, this question's basically also saying an ideal gas looks like that. So what Boyle was doing is P and V, if he had the moles constant and the temperature constant, right? So you would have to have, you know, your piston assembly, and you'd put it in a wonderful temperature control oven or air conditioner, whatever. So let's just say one of your first temperatures happens to be 273 Kelvin. So all he would have done is, for instance, he could, just put more and more pressure, masses on here to increase the pressure, and then he would measure what the volume did because I put more pressure on it. So you populate this. What he noticed is when you multiply these two values, he kept coming up with the same constant. We know the ideal gas law looks like this. So we've also seen, now let's say he did this one at 273 Kelvin. He'd repeat the experiment, but in this case, your assignment says, let's make your next one 773. Redo the experiment. What they found, and this is in all the books, is the lower the temperature, P. Now, you are asked to graph V versus P, which is fine. You get this hyperbola. And the lower the temperature, the tighter this turn is. As you increase the temperature, it starts to flatten out, right? So a lot of books will show this trend. So long story short, what you're asked to do is pretend you have an ideal gas, demonstrate Boyle's law, that as the temperature goes up, this is what the graphs are doing. So your job is to simply just graph these for an ideal gas. So the interesting thing is, if you go ahead and you put in 1 mole R, and then your first temperature is 273, this comes out to be this constant Boyle found, these 3 things multiplied together, comes out to be 22 decimeters times a bar. So the R value would be decimeters cubed is like a liter times a bar over a mole times a Kelvin. So the R that you would use, to my knowledge, would be 0.08314 liter times a bar mole per Kelvin. So that value of R times 273 gives you essentially that, assuming you have 1 mole in this apparatus. So what you'll do is you'll say, okay, pretend this now becomes your math equation. What if in math class they said your Y is going to be V, your X is P. So you would rearrange it to look like this. What if in math class they said Y, which is V, was equal to some constant 22.7 divided by X? What if math class asked you to graph this? So all you would do is pick a whole bunch of X's and record the Y's and make sure that you get for this height. And everybody knows in math, 1 over X looks like this. And as this number up here becomes bigger or smaller, it changes the in math, I was just saying, you could graph Y equals 1 over X, which is a normal hyperbola, and as a constant up top gets bigger, you change the shape of the curve here, right? But this is what you're asked to graph, but it'd be V versus P, right? So then, to move on ahead, think of what you're going to do here. So for your first graph at 273, this is your constant, and you're graphing this. This is your Y, and that's your X. But let's say you want to move on to the next one. 773 Kelvin. Well, PV equals 1 times 0.08314 times the new temperature, 773. And the number that comes out, imagine that, is 64.3. So now what you're going to graph is V equals 64.3 over P. So instead of using 22.7 up top, now it becomes that. And then when you go to the next temperature, you do the same thing. So all you're really doing is graphing different graphs of y equals a some constant over x. You're graphing 4 of them and you're stacking them, and it'll kind of do this, right? So in Excel, when you put your data points in, right, you can right click on this and it will fit it with the so for instance, your first one will be y equals 22.7 x to the negative 1. Your second one will be y equals 64.28 x to the minus 1, and so on. And it fits perfect. And it looks basically like this. So this is exactly what yours should look like when you're done. This is another exercise in populating the appropriate x and y values to simply graph these types of functions for the 4 temperatures. So that's question 5. And every single PChem textbook has this kind of picture in something like this, but it's nice when you do it yourself and graph it in Excel for yourself.